In the last video, we learned about the most important building blocks of a transformer network encoder. In this video, I will tell you about the missing details that were not relevant for understanding the overall workflow of the encoder, but which are crucial for model performance when optimizing the encoder. There are 4 missing functionalities that I didn't mention so far, and we will add these step by step to the encoder that we already know. Here you see the encoder from the last video that takes as its input an amino acid sequence of a protein where we encode every amino acid as a separate token. The first thing that we add to this encoder is a so-called residual connection around the attention block. On the next slide, we will look at what this is. So far, you see the process that we already know. We have a numerical vector representation for each vector in the input sequence. And we use the attention function to update each representation using information about the other representations in the input sequence. This is defined by the attention function we saw in the previous video. The updated vector EI is equal to the result of the attention function. Adding a residual connection simply means that after calculating the updated vector with the attention function, we simply add the original vector EI to this updated vector. This has the advantage of making it easier to train the encoder by addressing the vanishing gradient problem. Residual connections ensure that the gradients do not become zero or very close to zero during backpropagation when training the model for very deep architectures. On the other hand, it ensures that we keep the information from the input vectors and the model can still use this information very easily. As you can see, we not only add the residual connection for the attention block, but also to the feed-forward block, where this process works in exactly the same way. The next additional feature that we are going to look at is that we actually use a so-called multi-head attention block. This simply means that we apply the attention function multiple times in parallel. So let's look at it in more detail. As mentioned on the previous slide, multi-head attention means that we apply the attention function multiple times but with different parameters. Each of these attention functions are called a head. And for example, we could have 8 of such heads in one attention block. So let's have a look at how these heads look like. To update the embedding vector EI with head number j, we apply the attention function to this vector. Here it is important to note that in every head we use different matrices WE, WK, and WV to transform the embedding vectors that we use as the input for the attention function. If we wouldn't do this, we would simply apply the same attention function h times. After we passed vector EI through all h attention heads, we want to combine the resulting vectors in a single vector that is then updated, or our updated representation for the vector EI. We can achieve this by simply concatenating the resulting vectors, which means that we attach the vectors that are the results of calculating all h head functions. And finally, we multiply this resulting vector by a matrix WO, which is simply a linear transformation. When we do this, we have to keep in mind that in the end, we want to have a vector that has dimension d again, which is the same dimension of the vector EI that we used as the input for the multi-head attention function. So let's look at the dimensions of the matrices and the resulting vectors. In order to get a vector in the end that has the same length d as the initial vector EI, we want that each attention head produces a vector of reduced size. This reduced size is d divided by the number of attention heads h, and we call this reduced dimension m. To achieve this, the matrices WE, WK, and WV must have dimension m times d, because multiplying a m by d matrix by d-dimensional vector results in a m-dimensional vector. And if we then concatenate those h vectors of dimension m in the step below, we get a vector of dimension d again. And if we multiply this vector then again by a d times d matrix WO, we finally get a vector of dimension d, which is what we wanted. But why do we need multi-head attention and cannot simply apply a single attention function? Multi-head attention allows the model to focus on different parts and aspects of the input sequence for each attention head. Each head can specialize in attending to different types of information or pattern within the input, leading to more informative representations. And due to the reduced dimensions of each head, the total computational cost of the multi-head attention is similar to the computational cost of a single head attention with full dimensionality. The next thing that we add to our encoder is layer normalization. We apply this layer normalization to the output vectors that we get from the multi-head attention block. Without layer normalization, the values in the resulting vectors can have a wide range of positive and negative values. And by applying layer normalization, we can ensure that the values of each vector have a much smaller range that are centered around 0. Ensuring that the values are in the same range makes the training more stable and faster. We will now look at how layer normalization works by looking at a small example. For practicality, let's assume the dimension of the vectors that we get as the output of the multi-head attention is very small, in this case 3. And we assume that we are processing a sequence that consists of only 2 tokens, and we are currently processing only one sequence. Then the output of the attention function is 2 token representations, E1 and E2, both of dimension 3. We can now normalize each of those vectors by calculating the mean of both vectors and the standard deviation of both vectors separately. So we see the first vector has a mean of 2, the second vector has a mean of 1. And the first vector has a standard deviation of approximately 2, and the second vector has also a standard deviation of approximately 2. Now we normalize each vector by subtracting the mean mu1 from E1 and dividing by the standard deviation sigma 1. This gives us a vector that has mean 0 and a variance of 1. And we do the same for the second vector using mu2 and sigma 2, resulting in normalized vectors. Layer normalization now allows the model to rescale those normalized vectors by adding learnable parameters gamma and beta that have the same dimension as our vector representations. We calculate the Hadamard product of gamma with the normalized vectors. This means we multiply the first entry of gamma with the first entry of the normalized vector and use this as the first entry of the resulting vector, and so on. And then we also add the vector beta to the resulting vector. Here it is important to note that we rescale all vectors that come out of our attention head using the same parameters gamma and beta. This rescaling with gamma and beta gives the model the flexibility to learn and adjust the scale and the shift of the normalized data, allowing to scale to a distribution that is best for effectively training the model. As before, for the residual connection, you can see that we not only apply layer normalization to the output of the attention block, but also to the output of the feed-forward block. We are now coming to the last missing step for getting the full encoder architecture. Instead of applying the attention block and the feed-forward function only once, we have multiple layers of these attention and feed-forward functions. We have seen that the first set of attention block and feed-forward block produces a numerical vector for each input token. These vectors have the same number and dimension of the vectors that we receive from the input embeddings and positional encoding. So we can simply use these vectors that come out of the first layer of the encoder as the input for a second layer of the encoder that again consists of the same building blocks that you can see here, but with different learnable parameters. We do this to further update and improve the token representations, and we do this for a predefined number of times. And the vectors that come out of the final encoder layer are our final token representations. When we looked at how to update embedding vectors from an input sequence using the attention function, we only looked at how to update a single embedding vector at a time using this function, which you can see on this slide. However, the computations of updating different embeddings do not depend on each other, so we can do these computations in parallel. Instead of using only one embedding EI as input to the attention function, we can use all the embeddings of the input sequence stored in a matrix Q. This results first in an attention score matrix, where each row stores the attention scores for a specific embedding, or more precisely, row number I stores the attention scores for the embedding EI. By multiplying these attention scores by the matrix V transpose, we get a matrix of dimension n times d, where n is the number of tokens in the input sequence. This matrix stores the updated embeddings for all embeddings of the input sequence. And we learned in the last video that we first perform linear transformations to the input of the attention function. And we can do this in exactly the same way as before, even when performing all computations in parallel.